Hello everyone and welcome to lesson 2.1, motion, part 1 of 2. Alright, so in this video we're going to be going through the PowerPoint. I hope you already printed out the student version. So while you watch the video, make sure you fill in the student version of the slides. Again, writing things down puts them into your long-term memory. The first slide that I like to start off with is this one, like I mentioned last time, the one that has the data booklet reference in red. So if you can grab your data booklet, always have it with you when we go through the lesson, whenever you go through the homework, okay, and go to the page with the equations core. Since this is section 2.1, you're going to go to box 2.1, and sure enough, the equations that we are going to be covering today and in the next part are here. Okay, so just make sure you know where to find it. Excuse me. All right, let's go back to the slides. All right, these are all the IB pathways. All right. Now, I did mention before that we're going to talk about all of this, distance, displacement, speed, velocity, acceleration. So here we are, we're finally getting to it. So let's start off with distance and displacement. Now, there are a couple branches of physics that usually start a physics course. Mechanics, kinematics, and something called dynamics. The first unit in grade 11 physics is generally kinematics. That's where we introduce things like distance, displacement, speed, velocity, acceleration. And then the introductory unit in grade 12 physics is called dynamics. That's where we investigate things like forces and, well, more specifically, exactly Newton's laws and how they apply to certain problems. So Galileo had a big hand in kinematics. Newton not only had a big hand in calculus, but also in dynamics. So these two are known as the two pillars of mechanics. So kinematics and dynamics are both under the umbrella of mechanics. Excuse me. All right. So like I mentioned on the earlier slide, kinematics, we're going to be studying displacement, velocity, acceleration, distance, speed. All right, so consider Freddy the Fly and his quest for food. So there is a melted chocolate chip, and Freddy the Fly is going towards this chocolate chip. And he's going to have to move in a certain direction through a certain distance. Let's say that distance is 6 meters. Okay. So if we incorporate the direction, this is a displacement. But if we just quote the distance without a direction, that's a scalar quantity, and that's just distance. Excuse me. Okay, so distance is how far something has traveled, no direction. Displacement is, in addition to how far you have traveled in a net result, what direction did you travel in? So while sometimes displacement and distance have the same magnitude, they do not always have the same magnitude. So I have to keep repeating that. Right? In this case, the distance and the displacement do have the same magnitude because Freddy the Fly only moved in one direction along a straight line. Okay, so displacement, here's the magnitude, and here is the direction, positive x direction. All right. Now, we showed in the last video that if you are dealing with linear motion, so just forward, backward, left, right, up, down, only a pair of those, you can put a plus sign for positive x direction and a minus sign for negative x if it's a vector. Okay? All right, so we saw some of these examples in the previous video. We had a ball undergoing a displacement to the right and also undergoing a displacement to the left. So displacement A, 15 meters to the right. Displacement B, we were at 20 meters to the left. So to the right, we put a plus sign, and for the left, we put a minus sign. So if you put a plus, that means you are now considering this to be a displacement. If you don't put any sign, I know that it would still technically mean positive, but you have to put the plus sign to indicate that it's a vector. So it's implied that you recognize that there is a sign there. Okay. The distances, of course, they're just the absolute values of these numbers, 15 and 20 meters. Okay. Oh, one more thing. So just again, remember that displacements, these are vectors. Distance is a scalar quantity. Okay. Now, as for labeling, right? Because we always have to be able to label and use labels in our problems for different quantities so that we know what we're dealing with. And oftentimes we're going to need subscripts. So x2, that is the final position of an object. x1 is the initial position of an object. Some physics textbooks, instead of using 2 and 1, they use f and I for final and initial. You can use that. You can use the numbering system. It's whatever you prefer. Right? So now the change between x2 and x1, so x2 minus x1, we call that delta x. This triangle symbol in the front, we call that delta, D-E-L-T-A. Delta means change. And whenever you see the symbol delta in front of any physics quantity, whether it's x, whether it's v, whether it's t, whatever it happens to be, it means change in that quantity. And it's always going to be equal to the final of that quantity minus the initial of that quantity. Okay. Now, delta x is x2 minus x1 just because the letters match up, but usually we just call that s. This is the displacement. The final position minus the initial position. We're going to do some problems that involve this. For IB students, they have to be careful because the delta, they study uncertainties. So in section 1.2, which the non-IB students don't necessarily cover, we don't make a huge distinction in the way the symbol looks. The uncertainty symbol looks like the delta symbol. S, here S is a quantity, it's not the label for the unit, right? So for time, S is seconds. For the quantity in the formula, it's displacement. Okay? Okay, so let's do a problem. Use the displacement formula to find each displacement. Note that the x is equal to 0 coordinate has been placed on the number lines. All right, so for displacement A, let's start with this top case first. So displacement is final position minus initial position. Now each of these ticks, right, on the number line represent 1. So let's see, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my final position is red spaces, or 8 rather, sorry, I think that was 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's right. 10 meters to the right. And our initial position was 1, 2, 3, 4, 5 meters to the left. So minus 5 meters, and here we have positive 10 meters. Now displacement is final position minus initial. This is our final position, right? We start with the blue and then we move towards the red. Excuse me. So positive 10 meters, and then subtract negative 5, right? And you guys know how to deal with that. You would have learned that in grade 9, okay? So positive 10 minus negative 5. When you subtract a negative, you add it. So 10 plus 5 is 15. And we put the plus sign in front to indicate the displacement is 15 meters to the right. And sure enough, if you just look at the picture, if you start at the blue and you move 15 spaces to the right, or 15 meters to the right, you end up in the red position. We can do the same thing for this bottom example here. Notice that the blue and the red are lined up, so that's 10 meters. This was 5, so that's 6, 7, 8, 9, 10. So we have minus 10 and we have positive 10. So displacement is final position minus initial position. So negative 10 minus positive 10. Negative 10 minus positive 10 is negative 20. All right, so from where you start, you move 20 meters to the left in the minus direction. Hence, you get to the position of the red dot. Okay. Now let's talk about speed and velocity. We talked about distance and displacement. Velocity is represented by the letter V, and it tells us how fast something moves through a displacement. Velocity is displacement over time. This is how you calculate it. V is equal to S over T. Excuse me. Okay. Now, since S is displacement, is the change in position, you can also represent that with delta X. Usually I prefer to use S, although sometimes X is used if it's a linear motion. So that's, again, up to you. Let's try this question. Find the velocity of the second ball, ball B, if it takes 4 seconds to complete its displacement. So if you need to, you can flip back to that slide, but the displacement for ball B was minus 20 meters. So if it covered 20 meters to the left, so the displacement being minus 20 meters in 4 seconds, so you're looking at this formula, the numerator would be minus 20 meters and the denominator would be 4 seconds. Now, negative 20 divided by 4 is negative 5, right? So that's where we're going to end up with here. Negative 5 meters per second. Well, this is the other thing. This is another way to show units. Instead of writing -5m/s, so for meters per second, we can also remember our exponent laws, that if you have meters times seconds to the -1, that's the same thing as having the seconds in the denominator. Whenever a quantity or anything, whether it's a number or a letter, if it's raised to a negative exponent, you can make that exponent positive by simply changing its position from numerator to denominator or denominator to numerator. So just make sure you're comfortable looking at the units like this as well. Okay. So -5 meters per second. Now, since we're calculating velocity, velocity is equal to displacement over time. Velocity is a vector. Displacement is a vector. Time is a scalar. That means the direction for velocity comes from the direction for the displacement. Okay. So this is what we've already covered in the previous case. Now, so we said velocity is -5 meters per second. We know that the ball was undergoing linear motion. And so we can simply remove the minus sign and say that the ball's speed is 5 meters per second, right? So we don't indicate any kind of direction. Now, speed is distance divided by time. Remember that velocity is displacement over time, and those two are often not the same thing. A runner travels 64.5 meters in the negative x direction in 31.75 seconds. Find her velocity and her speed. So again, in this case, they're running in a line. So your displacement and your distance will have the same magnitude. All right, so for distance, you're going to do 64.5 meters. You're going to divide that by the time of 31.75 seconds, and you're going to get the speed. Okay. For velocity, since you're traveling in the negative x direction, you just stick a minus sign in front of the 64.5. Okay. And you're going to get the final answer, -2.03 meters per second. So therefore, you just take off the minus sign, and you have the speed. Again, I'm going to keep saying this till it gets annoying. These two are usually not the same value, so please be careful. All right, acceleration. Acceleration is the change in velocity over time. Okay, so change, remember, is represented by the Greek letter delta. Okay, so that's change in velocity over change in time. Now, acceleration we can also represent like this. This is change in velocity right here, v minus u. So while v does mean velocity, we're going to now break that down into two different letters, u and v. U is the initial velocity, v is the final velocity. Now, just before we move on, I want to show you something. A way to remember all of these letters. I want you to remember the following, I guess we can call it an acronym, SUVAT, okay? It's just a way for you to remember. S is displacement. It can be used as distance too, but you have to be careful when you use it in the formula. S is displacement. U is initial velocity. V is final velocity. A is acceleration. And T is time. And just to remind ourselves, displacement is measured in meters. Velocity is meters per second, or ms to the -1. Final velocity, it's still a velocity, ms to the -1. Acceleration, ms to the -2. And time is measured in seconds. Okay. So SUVAT, remember that acronym. Let's go back to the slides. All right. Yeah, so at the bottom here, it's just again reiterating what I just said. Instead of using subscripts of numbers, sometimes some books use letters. It's up to you. Okay, let's try this problem. A driver sees his speed is 5 meters per second. He then simultaneously accelerates and starts a stopwatch. At the end of 10 seconds, he observes his speed to be 35 meters per second. What is his acceleration? So I hope you have the question on the slides in front of you. If you don't, please pause the video and write it down, because I'm going to switch to the piece of paper and we're going to solve this problem. Okay, so it's better if you can see the problem and see where I'm getting the information from. Okay, so let me just do that. So switch screens here. All right, let's do this example. Okay, so the driver sees that his speed is 5, he accelerates, and then after a certain time, he has a new final speed, which means the initial speed is 5 meters per second. Okay, this is how I want you to always set up your problem. Not only is it going to set you up for success, but it is a way of you showing your work and essentially guaranteeing that you're going to get full marks on this problem. All right, so my initial velocity is 5 meters per second. I know that my final velocity, which is v, is 35 meters per second. And this acceleration occurs over a 10-second time interval. Now you might notice on the problem that there is a dot like that after the 0. If you're wondering why that is, that has to do with significant figures. If you're studying chemistry, most certainly you are studying significant figures. All that decimal means is that that 0 is now significant, and now that this number is more meaningful than just writing the 10 without the decimal. If you are interested in learning more about sig figs or significant figures, let me know and we can always go into it. Okay, so this is what's considered the given pile. Okay, this is what we've been given in the problem. What are we looking for? What's required? We're looking for acceleration. So A, given, required. Okay. Now, which formula can we use? This is when you grab your data booklet and you just, well, figure it out. You got box 2.1, you have U, V, T, and you need A. Okay. U, V, T. So if I actually look at the first one there, it might be a bit hard to see based on this camera, but if you have the formula sheet in front of you, it should be okay. The first formula here is V equals U plus AT. And so it has 3, I have 3 out of the 4 things in that formula, and I'm missing one of them. So that's perfect. So I'm going to write that formula down next. V is equal to U plus AT. Okay, so this part is called the analysis, which formula you're going to use. So given, required, analysis. The next part is solution. Now, we are not solving for V here, we're solving for A. Right? So we have to actually rearrange this for A. All right, so what we're going to do is we're going to first subtract U from both sides. So V minus U equals AT. By the way, you have to make sure that you are very good at rearranging equations, as complex as they are, because that is an absolutely essential skill you need in this course. Now, in order to get A by itself, A is being multiplied by T, so I have to divide it by T. But if I divide the right side by T, I have to divide the left side by T. So A is equal to V minus U divided by T. And sure enough, check it out. If you have V minus U, final minus initial velocity, guess what? That's delta V. So delta V over T, that's the very definition of acceleration. Change in velocity over change in time. So you could have just as well started with this formula and obtained this. But everything in time. Okay, so now this is moving into the solution phase. And this is, of course, continuing. Okay, so A is equal to V minus U over T. That's the formula that I'm using. Okay, so here are my values. 35 minus 5 divided by 10. 35 minus 5 is 30. 30, now in the numerator, I have units of meters per second. In the denominator, I have units of seconds. So if you look, I have seconds to the minus 1 in the numerator. All right, so if I have seconds in the denominator, this is going to become seconds to the minus 2 in the numerator. So 30 divided by 10, that's 3. So 3 meters per second squared. That is the acceleration. All right. Now usually, so this is also part of the solution. Solution continued. Usually there's another part here and we say, therefore, the acceleration of the driver is 3 meters per second squared. And this also goes in a box. Now this part we call paraphrase. What I'm trying to do right now is show you the proper algorithm for showing your work and, well, successfully arriving at the final answer. So what I have essentially done here is I have solved this problem using something called the grasp method. If you take the first letter of each of these words it spells the word grasp. G-R-A-S-P. Okay, the grasp method is a fantastic way of showing your work and also organizing yourself for success. So the way in which you have to do this, so always start off by writing down what you're given in the problem, what's required, what you're looking for, analysis, which formula are you going to use, solution is the longest part. This is where you plug in the values and you come to a final answer. Paraphrase, that's your therefore statement. Okay, so you say therefore, whatever it is, what is, this is the final value, and you stick that in a box. Now, what you don't need to do, you don't have to label each section as given, required, analysis, solution, paraphrase. You just have to do it. I did this the first time so that you could see what's required for full marks. Now, this question didn't really require a picture, although we could have drawn one. In later problems, you'll see that it will be absolutely vital to draw a picture and help us solve the problem. Okay, let's go back to the slides. Okay. So we went through the solution already. There we go. All right, why is velocity a vector? And why is acceleration a vector? Well, remember, by definition, velocity is displacement over time. And since displacement's a vector, therefore velocity has to be a vector too. Velocity, as we saw on the slides earlier, it inherits its direction from displacement. And likewise, acceleration is velocity over time, or change in velocity over time. So whatever direction the change in velocity has, the acceleration inherits its direction from that. So that's the answer to this slide. So if you need, you can pause the video right now so you can write down the answer. All right. Determining instantaneous and average values for velocity, speed, and acceleration. Okay, those of you that recognize what the police officer is holding in this picture, this is what's called a radar gun. So police officers use this to determine cars' speeds, whether they're on the highway or on the street. Radar works pretty well, but sometimes can make mistakes. Laser is essentially foolproof. All right, so consider a car whose position is changing. The patrol officer is checking its speed with the radar gun, and so the radar gun measures the position of the car during each successive snapshot shown in yellow. Okay, so this car is speeding forward. And you're going to see these successive snapshots now. Notice what's happening between the spacing, right, between each successive snapshot. How can you tell that the car is speeding up? Think about that. Pause the video if you'd like. Well, you know that each snapshot is successive, so we can assume here that he's pushing the trigger on the radar gun relatively at a frequent rate. So maybe every 1 second or every 1.5 seconds he's pressing it. However long, it's successive. But we notice that despite the interval of time between these yellow marks being the same, the car is covering more and more distance every time. More distance covered in the same time interval means that you must be traveling faster, right? So this car is in fact speeding up. What are you assuming about the radar gun time? We're assuming that he's pressing the button at regular time intervals. Okay, now we can label this, right? So each interval here, we're going to label x1 through 4, and the time interval between each is delta t. Now that delta t is the same, which is why we don't label it as delta t 1, 2, and 3, because it's the same delta t. When the values are different, you have to distinguish them by putting different labeling subscripts. Now we have different velocities within each of these bands, velocity A, velocity B, velocity C. Now we can calculate the velocity. Remember, velocity is change in displacement or change in position over time. So velocity A is going to be x2 minus x1 divided by the time. Velocity B is going to be x3 minus x2 divided by the time. And velocity C is going to be x4 minus x3 divided by the time. Now, if you just look at this interval from x2 to x3, we're saying that the velocity of the car is vb. But in reality, when a car is speeding up, imagine looking at the speedometer on the dash. The needle doesn't suddenly jump from one speed to another. It's gradually increasing. It gradually rotates in a clockwise manner as you increase your speed. Or in the other direction, if you're decreasing your speed. That means that every single moment in time, your speed or your velocity is different, right? So, but what this picture is demonstrating is that the velocity only occurs 3 different ways. So what we have to remind ourselves is that this VB, this is an average velocity between points x2 and x3, right? It's not the instantaneous or exact velocity. It is the average velocity or average speed, okay? Just like VA and VC. So then think about that for a moment. If this is the average speed, how can you get a more accurate picture? What can you do? Pause the video if you would like to go ahead and think about that. Okay, so in order to get more precise information, we would have to take more snapshots. So the cop would have to be pressing that gun much more frequently, right? If you have smaller intervals of time, and we know that these intervals of time are still the same, well, we can get a more accurate picture, right? So now if you look at that orange band, we're going to have a different what would it be? X1, 2, 3, X4, and X5. You would have a different delta t, and this would be a more accurate picture. Now, how would it be possible to get the exact velocity or the exact speed at a certain point? And it is possible, absolutely. You can see that if we make the time intervals smaller, we get a more accurate picture. So the more time intervals you put, the more accurate the velocity at a certain band becomes. So theoretically, if you were to put an infinite number of bands here, then the time interval between each of them would reach 0. That is what's called a limit. Limits are discussed and they are studied in calculus. So if you study calculus, which I hope you do, you will learn all about limits there and all about derivatives. If you are interested in learning about that now, please feel free to let me know. Okay. Now, it's the same for acceleration. Since acceleration is change in velocity over change in time, we can also find a more precise acceleration by taking a smaller and smaller time interval. So acceleration equaling to delta v over delta t, that is the instantaneous acceleration, for our purposes anyways. Also, something I should mention, in all of our calculations, our displacements, our velocities will be changing. What's going to be constant for us is our accelerations in terms of calculations. All right, so here are the 4 kinematics equations. And like I keep mentioning, I hope you have your data booklet in front of you. Those 4 equations are right here in box 2.1. So make sure you constantly refer back to this. They're here on this slide as well. And again, you can only use them if the acceleration is constant. Now, the next 3 slides in your booklet, we're going to skip them. Okay, so before we get to that, actually, there are names for these formulas. I'll be upfront with you all. I'm not going to be using these names for the formulas. It just seems like extra work. Once you start getting into the flow of using these formulas to solve various problems, you're not going to worry about what the name is. You're just going to worry about what variables you have, what you're looking for, which equation can help you solve it as fast as possible. And so if you want to learn the names, you can, but we're not really going to focus on them. Okay, so 3 slides later, we're going to skip the previous 3 slides. So here are the formulas, and we're going to be practicing these equations. Now, there's a very special acceleration that we have to talk about, and that is called the acceleration due to gravity. Sometimes it's called freefall acceleration, and it's given the symbol g. Be careful, do not call this gravity. Yes, it is the acceleration due to gravity, but a lot of students call this gravity just because it starts with a G. If you call this gravity, you will lose marks because your answer is not concise and it is open to error. Okay? Acceleration due to gravity and gravity are different things. They have similarities, but they are not the same thing. All right, let's determine the acceleration of free fall experimentally. So let's say you stood on top of the Leaning Tower of Pisa and you decided to drop a bowling ball. You know that its velocity would speed up as it headed towards the ground, and of course you would make sure that there was no one standing there below as you dropped it. If you were to drop a tennis ball, well, would it reach the ground faster than the bowling ball? Would it take the same time, or would it take more time? Okay, so think about that for a moment. tennis ball versus a bowling ball. And if you really want to make it interesting, you can compare those two to a ping pong ball. Okay, if you need more time to think about it, pause the video and really consider what's happening here. But a lot of people would be surprised to learn that all three would hit the ground at the exact same time. Most people are under the misconception that things that are heavier fall faster. And in fact, this is what Galileo and many other scientists and individuals used to believe. And I guess that is based on a bit of logic because from our experience, a lot of times heavier things do fall faster, or at least they seem to fall faster than lighter objects. For instance, if you've ever taken a feather and dropped it and you drop a textbook next to it, the textbook definitely reaches the ground first and it is definitely more massive than the feather. But it's not because of their difference in mass that one falls and hits the ground first. This is the reason why the bowling ball and the ping pong ball will hit at the same time. It has to do with more than that, and it has to do with something called air resistance, which we'll talk about in a few slides. But in reality, every single object accelerates at the same rate, and that is the acceleration of free fall, also known as the acceleration due to gravity. As long as there is no air resistance, all objects will fall at the same rate. The reason why a feather will appear to fall very slowly is because it has a lot of spaces in between all of its fibers, and so air can get caught in these obstructions and it can slow down the descent of the feather. The reason why the bowling ball and the ping pong ball fall at the same rate is because despite their difference in mass, they're both going to interact with the air more or less on an even level. And if you really want to get into it, the air will actually affect the bowling ball more because there's more surface area. Okay? Now, actual experiments of this have been done where they drop a bowling ball and a feather side by side in what's called a vacuum chamber. If you recall, we talked about what a vacuum was earlier in our course. A vacuum is a region of space where there are no particles. So what some scientists will do is they'll take a chamber and they will empty it of all particles. Of course, no one will be able to stand inside at the time because there's no oxygen to breathe. But then they show a feather and a bowling ball being dropped side by side, and they do in fact hit the ground at the same time. It's absolutely spectacular. In this slide, we're going to experimentally determine the acceleration due to gravity by comparing an apple with a feather. And this is a time-lapse snapshotted series of pictures. Okay, so there are several pictures taken at equal time intervals of how this apple and this feather fall in a partial vacuum. So it's close to a vacuum. Now what we're going to do is we're going to pick a convenient location on the apple so that we have a proper measuring position to compare. So let's say the bottom of the apple. Okay. Now let's choose a scale. Okay. Earlier, the diameter, or well, maybe not the diameter, but the horizontal diameter of the apple was found to be 8 centimeters. Okay, so then we superimpose that scale on top of the entire vertical range here, so we can produce measurements. All right, don't forget, this is just a photograph. All right, so now we can estimate the position in centimeters of each image, starting off with 0. Just notice here, 0 doesn't start where it's first dropped, it starts a bit lower, so just keep that in mind. 0, minus 9, minus 22, minus 37, and minus 55 centimeters. Now, what I also know is that the time interval between each of these pictures is the same, and the time interval between each of these snapshots is 0.056 seconds. So what I'm going to do is put all of this data into a data table, so then I'll eventually be able to create a graph. Okay, so I'm going to have time in seconds, the y distance in centimeters. Okay, so the y distance, these are the numbers that were on our picture, 0, minus 9, minus 22, minus 37, minus 55. And the times, it's every 0.056 seconds. Okay, so if you double that, you get 0.112, triple that, quadruple that. All right. Now we're going to find delta t, delta y, and eventually v. The velocity is going to be the change in displacement delta y over delta t. Okay, so these are our last three columns. Now for delta t, remember delta means change. That means I have to subtract two time values from each other, a final minus an initial time value. I can't start with the first one because that's only one time value. I need at least two. Okay? The same with the delta y. I need two y values to subtract, and since there's only one in the first row, I can't have any value there either. And likewise, since v is going to be delta y divided by delta t, if there's no values for them, there's going to be no value for v. Okay? So the first row is blank. Now let's calculate the second row. For delta t, it's going to be delta t2 minus t1, 0.056. Again, t2 minus t1, 0.056. t2 minus t1, 0.056. And if you want, you can actually see it as t3 minus t2 or t4 minus t3, as long as they are consecutive. And sure enough, just as we would expect, since the snapshots are taken every 0.056 seconds, those are the intervals of time in our table. Now we do the same thing for the last piece. It's going to be the same number, and then we move on to delta y. So -9 minus 0 is -9. -22 minus -9 is -22 plus 9, which is -13. -37 minus 22, or minus -22, is -37 plus 22, which is -15. And finally, our last difference results in -18. Now for velocity. Velocity is, well, change in displacement, change in position over time. So -9 divided by 0.056. So we go ahead and do those calculations. Again, delta y over delta t, delta y over delta t, and finally delta y over delta t. Okay, so notice that the velocity is getting larger. Now the fact that there's a minus sign in front, that's just because it's moving down, and that's coming from y getting measured downwards, right? So this is implying that positive is the upward direction. Okay, we have our data table. Now let's graph it. We are going to create a velocity versus time graph. Now, something I want you to know, in case you don't know this yet, anytime you're told that it's a something versus something or other graph, whatever letter or quantity comes first, that's always on the y direction. The one that comes second is in the x direction. Okay, so we have time in the x and we have velocity in the y. Pay attention to how everything's done. Notice that a proper graph has straight lines, it has axes, labels, it has a proper scale. And notice, okay, so not only do you have a proper axes labels of velocity and time, there is a slash after each, and then the unit is placed after the slash. Please get used to producing your graphs like this as well. All right, so time, that's the first column here, and velocity, that's the last column. Okay, so independent variable is your first column, dependent variable is your last column. All right, so here are going to be my 4 data points. So 0.056 minus 161. First data point. Second data point, 0.112, comma, minus 232. Next, 0.168 minus 268. And last, 0.224 minus 321. Notice that those points pretty much form a straight line. Now, with real life data, it is not possible to get a perfect straight line. Right? Perfection is something that we aspire to. It is not something that gets achieved. Right? Perfection is always something that we are in the pursuit of. Something that I need to teach you right now, and you need to remember this throughout any course you do in math and science. I can't speak for the other sciences, but generally this is the case. Whenever you have points on a graph, do not ever connect the dots. This is the wrong thing to do. A lot of students always just try to connect the dots. In other words, draw a straight line from one point to the other and another straight line from the next point to the next. Do not ever, ever do this. Okay, it will be wrong in every single case. What you always want to do is either draw a line of best fit or a curve of best fit. For our purposes here, we're going to be drawing a straight line of best fit. And now, since the data is not perfect, the line is not going to go through the center of each dot, but you can see that more or less by eye, you can judge that this line approximates each point very well. These 2 points have the majority of their matter above the line, and these 2 points have the majority of their matter below the line. So this is very, very well done. Something that I want you to notice is that the initial velocity here, so when time is 0, initial velocity is minus 100 centimeters per second. And that is because of what I explained on the slide with the photograph. The reason the initial velocity is not 0 is because our first data point is not when the apple and feather were first dropped. It was a little bit later. And again, you can see that in the picture. So we see that the graph of velocity versus time is linear. And acceleration is the slope of the velocity time graph. This is a very important consequence. Okay, so let's keep going actually here for a second. So acceleration is the slope of this graph. So how do you find slope? You do rise over run, right? So the run is the x values, that's time, and you can create any size triangle you want, right? You just create it based on what's convenient for you, what data points you can conveniently read. So the run is 0.224 seconds, and the rise is minus 220 centimeters per second. So acceleration is change in velocity over change in time. So minus 220 centimeters per second over 0.224 seconds, and we get minus 982 centimeters per second squared. Now, if you are already familiar with the acceleration due to gravity, that is very close. And the reason why it's not exact is because this is not a perfect vacuum, right? We were told it's a partial vacuum. Not to mention our measuring instruments might be a little off. There's always room for uncertainty. Okay, this is a very important acceleration, which is why we give it its own symbol, at lowercase g, acceleration due to gravity. And all objects accelerate at acceleration due to gravity, especially when they are in free fall. Okay, so g is 980 centimeters per second squared. This is in the absence of air resistance, of course. If you have air resistance, this value will change. Now, usually we like to use this. G is equal to 9.80 meters per second squared. Sometimes in the slides, we're going to just use 10 to make the calculation easier. But in the homework, please use 9.8 because this is the accurate value to use. So this would actually be a good time for me to point something out. While we do have 9.80 in the slides, you can use 9.80 or 9.81. The reason I say that is if you take your formula sheet, if you turn to the first page, fundamental constants, there is a whole lot of constants here. The very first one is acceleration of free fall, Earth's surface. There's the symbol, lowercase g, and the value is about 9.81 meters per second squared. So there it is for you. So in case you forget, you can look it up. Okay. So in general, these formulas, the kinematics formulas that we saw that are in box 2.1 in your formula booklet, if you're dealing with an object that is in free fall, in other words, the only force acting on it is its force of gravity, its weight, then you can substitute minus g for a in those formulas. Something that I should explain here is the minus. Why is there a minus here? Well, acceleration due to gravity, gravity is an attractive force. We're going to learn all about gravity. Well, we'll learn a lot about it this year, but we'll learn considerably more about it next year in grade 12 physics. Gravity is an attractive force. So the Earth, being so massive, is trying to pull everything toward its center of mass, toward its center, okay, so toward the middle. So wherever you are on the Earth, if you zoom in on a person on the Earth, it's going to look like the force of gravity is pointing straight down towards the ground, right? Because that will technically be going towards the center of the Earth. So G, which is the acceleration due to gravity, this is in the same direction as the force of gravity, which is straight down towards the center of the Earth. Generally speaking, we define up as positive, and so down is usually negative. Although I should point out that you can change that. If you are doing a problem and you want to set down as positive, you can do that. And this is why I've explained in time and time again, when you solve problems, you have to define the X and Y direction, which is positive, because some people will want to set down as positive. Okay. Now, this cartoon character may or may not look familiar to some of you. This is Brain. Okay, so there is an old Warner Brothers cartoon called Pinky and the Brain. It's about two lab mice. One of them is very intelligent and the other one is very goofy. You can probably tell which is the goofy one based on the picture. The intelligent one, the Brain, he is always trying to find ways to conquer and take over the world. And so he needs to have those physics equations in order to do so. All right, so how far will Pinky and the Brain go in 30 seconds if their acceleration is 20 meters per second squared? Okay, so I hope you have the question there in front of you with the slides. We're going to move to the piece of paper and solve this problem. Okay. All right, so we have Pinky and the Brain. We want to know how far they will go. Okay, so in 30 seconds, so time is 30 seconds. Acceleration is 20 meters per second squared. And just leave a little bit of a space there. And we want to know how far they will go, s. Now, we have two pieces of information and we're looking for a third. And if you look at the formula, so let me just turn to that page. These formulas in box 2.1 all have 4 unknowns. And so what that means is in order to solve for a quantity, you need to have 3 out of the 4 pieces so that you can rearrange and isolate for the 4th. Here it looks like we've only been given 2 pieces of information, but there is another piece of information that you have to extract yourself that hasn't been given in the problem. Okay. Yes, they're accelerating, but think about what they started with. If you are in a car that is stopped at a red traffic light and the light turns green and you accelerate, so you press the gas pedal and you're traveling at 20 meters per second squared, 30 seconds later, you want to know how far you've traveled. Well, you have another piece of information there. You know your initial speed. And just as when Pinky and the Brain are in the rocket ship, the initial speed is 0. Okay, so that's the third piece of information. All right, so if we look at our formula booklet, we have U, A, T, and we need S. So the first formula has V, U, A, T. Since we don't need V, we're not using the first one. Let's see, the next one has S, which is what we're looking for. It has U, T, and A, which is perfect. So we're going to be using that second formula there. So S is equal to UT plus 1/2 AT squared. Now this is the nice part of this formula. When U is 0, this is what you get to do. U is 0, and so 0 times anything is 0. So that first product just disappears. So S is equal to 1/2 AT squared. Notice that I'm still following in the grasp solution method. I'm showing all of my work. This is what you need to do. All right, so we have 1/2. Acceleration is 20.0 and time is 30.0, and then we square that. So grab your calculator. So we have 0.5 times 20 times 30 squared, and that's 9,000. So 9,000 meters. So therefore, Pinky and the Brain will travel 9,000 meters, or you could say 9 kilometers. Okay, so that is done. Back to the slides. Now in the slides, it's solved using a slightly different way. Same final answer. I would like for the cases of having a full solution, please stick to the solution the way in which I have done it on the piece of paper. Okay, next, how fast will Pinky and the Brain be going at this instant? Go back to the page. At this instant, so that means now I'm looking for V. So I have T, A, U, and S. I need to find V. Well, now I can use that first formula that I had, right? V is equal to U plus AT. So here we go. V is equal to 0. I don't even need to write that. I could have just taken it out from the formula. 0 plus 20 times T, which is 30 seconds. All right, so grab your calculator. In fact, you don't even need to do this. You could do this in your head. 20 times 30 is 600. All right, so we have 600 meters per second. Since the question is saying how fast are they going, it's not asking for the velocity. You just give the magnitude with the unit. Therefore, Pinky and the Brain will be traveling at 600 meters per second. Okay. Good. Let's go back to our slides. Okay. Next, how fast will Pinky and the Brain be going when they have traveled a total of 18,000 meters? Okay. So how fast will they be going? Well, they're still accelerating, so they're probably going a bit faster now. Okay, well, keep in mind, if they've traveled a total distance of now 18,000 meters, that means it's taken them more time. That means that I cannot use the time from the original question, right? But I can use the original acceleration, right? Because acceleration is just saying how much they are speeding up by. That value is not necessarily changing. So 20 meters per second squared. I know that they still start off with a speed of 0. So I have SAU and I need to have V. All right. So looking at your formula sheet, SAU and you need V. If you look at the third equation, you have SAU and V is what you're solving for. So that's perfect. So we're going to use the formula V squared equals U squared plus 2AS. Again, U is 0, so 0 squared is 0, so that's gone. Oops, there we go. All right, so V is equal to the square root of 2AS. So V is equal to the square root of 2 times 20.0 times 18,000. Okay, 2 times 20 times 18,000 square root, and that is 848.5. So 848.5 meters per second. So therefore, Pinky, box that, Pinky and the Brain are traveling 848.5 meters per second after going 18,000 meters. Okay, let's go back to the slides. All right, so again, same solution, solved a little different. Okay, all right, so now we are done with Pinky and the Brain. Now we are looking at the Empire State Building. Used to be the tallest tower in the world. All right, a ball is dropped off the Empire State Building, which was 381 meters tall. How fast is it going when it hits the ground? All right, so let's go back to the page here. Now for this, I'm going to draw a picture. All right, so here's my ground. Here's the building. Okay, so this ball is dropped here, and it falls, and it hits down here. All right, now it's dropped. In physics problems, the word dropped is a keyword. When you see that word, you automatically know that the initial velocity is 0. And that's your clue. Now, this ball is falling downwards. So from where it starts to where it finishes, it undergoes a displacement of 381 meters down, right? So now I guess I shouldn't call that S because that'll get confusing with displacement, but my displacement is minus 381 meters. So minus 381 meters. Okay, the fact that I'm saying that down is negative means that I have to state that up is positive. So up is positive y. All right. So in this question too, it looks like I only have 2 pieces of information given to me, and I have to somehow find out how fast it's going when it hits the ground. There's a reason I left a space there, because there is a third piece of information there that you haven't necessarily been directly given, but something you can look up. Remember that when something is in free fall, it is accelerating and moving only due to gravity. That means we know the acceleration. The acceleration is minus g, so it's minus 9.81. I'm going to just use the value that's in the formula booklet, meters per second squared. Okay, so what am I doing? I need the formula first. All right, so I have S, U, A, and V. Okay, so S, U, A, and V, if we look at our formula sheets, S, U, A, V, right here, third formula. You're going to use that one. So v squared is equal to u squared plus 2as. U is 0, so that's dandy, that disappears. V is equal to the square root of 2as. So square root of 2 times negative 9.81 times negative 381. Notice the two negatives will cancel, allowing you to take the proper square root. Otherwise, you cannot take the square root of a negative number. In a calculator, I already know that the negative numbers are being eliminated, so I'm not even going to enter them. Square root, and we get 86.4. No, let's call that 86.5. Yeah, 86.5. Okay. 86.5, and that's meters per second. That is very fast, and this is why if you've ever stood on top of a very tall structure, no matter where you are in the world, there are usually signs that say do not drop anything from the top. Even if you were to drop something as seemingly innocent as a penny off the top, by the time it hits the ground, it's traveled a very large distance and it has gained a lot of velocity, and so it can actually kill someone. Now, that's not to say that something will just keep increasing speed indefinitely. So if you drop something from very, very, very high up, it's not as if it's going to necessarily reach infinite speed. We'll talk about why that is in a few slides. Okay, so we're dealing with the Empire State Building once again. This time we have to figure out how long it takes to reach the ground. All right, so same scenario, except now we're looking for the time. All right, so we have V, we have U, we have S, we have A. V, U, let's see, if we want to try to use what we were given originally, we have USA. Oh, there you go, USA. We have USA and we need to find T. Let's see here. Seems like the second formula is going to work. We have USA and then T's the unknown. So we have S is equal to ut plus 1/2 at squared. U is 0. That's nice, that goes away. Just want to point something out here. If u wasn't 0, it's not a big deal. T is going to appear twice, once as a linear and once as a quadratic. That means that you would eventually have to solve the quadratic formula and determine what the roots are of that equation to find out what T is. Just something to keep in mind. Okay, so we are looking for time. So rearranging this equation, so right now we're left with S is equal to 1/2 at squared. Rearranging for T, first thing I'm going to do is multiply both sides by 2. 2S is equal to at squared. Now divide both sides by A. 2S over A is equal to T squared. And finally take the square root of both sides. So the square root of 2S over A is equal to T. Now, when you take the square root of something, you always end up with a positive and negative root. But it does not make sense for time to be negative, so we only keep the positive root. All right, what I would like you to be able to do, hopefully soon, is be able to get from this equation directly to this. So being able to rearrange it in your head and getting to this point. It's very important, and it will save you a lot of time. All right. So T is equal to square root of 2S, so minus 381, divided by A, which is negative 9.8. Once again, the negatives cancel. So 2 times 381 divided by 9.8, square root, and we get about 8.8 seconds. Okay. Therefore, it takes the ball 8.8 seconds to fall to the ground at a speed of, or rather I should say, reaching a speed of 86.5 meters per second. Okay, so that's the Empire State Building problem. Let's go back. All right, in this scenario, we have a cheerleader being thrown up into the air. So a cheerleader is thrown up with an initial speed of 7 meters per second. How high does she go? Now, this problem is similar to how we would solve a problem if you were just throwing a ball into the air. Okay, so the ball would have an initial velocity at which it's thrown into the air, and we would have to figure out how high the ball goes. It just is more interesting when you're throwing a cheerleader, because that takes a lot of coordination and strength. So we have our cheerleader, and they're throwing upwards. Okay, so their initial velocity is not 0, it's 7 meters per second, right? Of course, the people have to put some kind of effort. Now, the cheerleader gets thrown up, gets to a certain maximum height, and then starts to fall back down, right? Now, while the cheerleader is at the top, think about what their velocity is. And think about at which point throughout the cheerleader's motion is her velocity the highest. And the answer is when she's first thrown up and when she's on the way back down, right? So she's traveling at 7 meters per second up, but gravity is slowing her down, and it's slowing her down at a rate of negative 9.81 meters per second squared. So she's slowing down from 7, so she's hitting 6, 5, 4, 3, 2, 1, and then 0, right? The point at which she hits 0 is when she's at her maximum height. And then she starts to increase her velocity. She starts coming back down, right? And her velocity is increasing because of gravity. She's moving down and the acceleration is down. So now she hits 1, 2, 3, 4, 5, 6, 7 on the way back down. Okay, so the velocity on top is 0. So if I call it v, that means the only circumstance I'm considering is from start to the maximum point. And since we just want to find out how high she goes, well, that's the S value I need, right? I just need the S value when v is 0. So that means I have U, V, A, and I need S. So looking at my formula sheet, I'm going to be using the third one, U, V, A, and I need S. So V squared equals U squared plus 2AS. Okay, so V is 0, so that's gone. We're looking for S, so what I'm going to do is take the U to the left, so negative U squared equals 2AS, and then you're going to divide both sides by 2A. So this is negative U squared over 2A, and all I did was I just switched the sides. I brought the 2AS to the left and the negative U squared to the right. Okay, so negative 7, oh, and I can't square the negative because that's out in front. Negative 7 squared divided by 2A, so 2 times negative 9.81. So notice the negatives are going to cancel, so just cancel those. 7 squared is 49. 49 divided by 2 times 9.81. So that's let's call that 2.5. 2.5 meters. So therefore, she goes 2.5 meters into the air. Therefore, the cheerleader is throwing 2.5 meters into the air. Okay, I hope that's okay. Back to the slides. Now, if any of you have ever traveled to France, you may have seen or even been on this amazing feature of engineering. Okay, it's called the Millau Viaduct. It is the highest bridge in the world. And as I recall, it was a joint effort between 2 European countries that allowed it to be built. Okay, so actually, yeah, we're going to solve this ourselves. So a ball is thrown upwards at 50 meters per second from the top of the bridge. How fast does it hit the ground? Okay, let's go to our page here and solve this. Okay, so let's see how we're going to do this. Let's draw the bridge like this, and we've got the poles holding it up. Okay, so a ball is thrown upwards, so it's thrown up first, and then it comes down and hits the ground, right? So it starts on the bridge, gets thrown up, and then falls and hits the ground. it's thrown up at 50 meters per second. Now, I realized that in this previous example, actually, I need to make a correction to the solution because I didn't actually state the positive direction here. So positive is up here. And here I have to define a positive direction as well. I'm going to let positive here also be up. Okay, so positive being up. I haven't really been labeling these as X and Y, and the reason for that is so far all of these problems are really and truly one-dimensional. We haven't really gotten into the two-dimensional problems yet, and I guarantee that when we do, I will start labeling them more consistently with subscripts, X and Y. Okay, but for now, up is positive. So that means the initial velocity of the ball is 50 meters per second. Now, this distance is 300 meters, right? But the ball is not traveling 300 meters. It goes up and then it comes back down. But what you have to understand is it doesn't matter that it travels through a longer distance. What we care about is the displacement. Displacement means the change in the final position minus the change in the initial position. Here is the final position. And you know what? I'll call initial position I instead of S, so it's not confusing. I is on the bridge and F is below the bridge on the ground. So from where it starts, it undergoes a displacement of 300 meters down, okay? Regardless of what it does up in the air, from where it starts to where it finishes, it's a difference of 300 meters down. And so you can see that displacement value would be the same even if this ball was dropped or if it was thrown down. The S value would be the same, but then other values would be different. Okay, so U is positive 50, S is minus 300 meters, and we want to know how fast it hits the ground, V. Okay, again, I've left a space there because we have another piece of information. This ball is moving only under the influence of gravity. So it is moving at minus 9.81 meters per second squared. Personally, I don't keep replacing the A with the G. I just understand that it is acceleration due to gravity, and I replace it with the correct value. So we have A, S, U, and we need V. A, S, U, and we need V. Third equation looks right. Okay, so here we go. V squared equals U squared plus 2AS. Okay, nothing is 0 here. So V is equal to the square root of U squared. So that's 50 squared plus 2A minus 9.81 times S minus 300. Okay, grab your calculator. So 50 squared plus 2 times, now negative times negative is positive, so I'm not even going to enter that here. 2 times 9.81 times 300. And we're going to square root that. So that's 91.6 meters per second, approximately. Okay, so that's moving incredibly fast. All right, let's go back to the problem. Oh, something I should point out. Even though here in the final answer there's a negative sign, it shouldn't actually technically be there. I should adjust that. The reason is the question doesn't say what is its velocity as it hits the ground. It says how fast does it hit the ground, and that means the question is specifically asking for speed, not velocity. Okay, so it's the same scenario. How long is it in flight? Okay. So now we're looking for the time interval as well, T. So now we have USA, and we are looking for T. All right, so let's see, USA and T. Now, granted, if you use this formula, it's true you're going to have to use solve a quadratic, which is fine. It's not a big deal. But there is ways to make that a little bit simpler. And although usually I don't recommend doing this, in this case, it probably is in your better interest. You can use the V value along with a combination of these other pieces to find time. And just because this way you won't have to solve a quadratic. So we have USAV and we have to find T. So we can just use the first formula there. V equals U plus AT. Okay, so V is, now this is where you got to be careful. The V in this formula is velocity. You can't plug in 91.6. Remember that upward is positive. Yes, this is the speed, but the velocity, remember, it's going down. So the velocity is negative 91.6. And so that's what you got to plug in over here. So be very careful. So that means if I want to rearrange this for time, it's going to be v minus u equals a times t, and then divide both sides by a. V minus u divided by a is equal to t. So t is equal to v, which is negative 91.6, minus u. Remember, u is positive because the ball's initially thrown up, divided by a, which is negative 9.81. All right, now I'm going to put the negative signs. Let's do it like this. Minus 91.6 minus 50 divided by negative 9.81, 14.43. Okay, 14.43 seconds, or 14.4 seconds. So therefore, the ball hits the ground at a speed of 91.6 meters per second and takes 14.4 seconds to do so. Okay. Let's go back. Okay. Sketching and interpreting motion graphs. So we actually looked at the velocity time graph, and we already came to the conclusion that the slope of the velocity time graph is acceleration. Now, the slope of a displacement time graph is the velocity. We also saw that. Now we're going to look at some deeper analyses of these graphs. Okay, suppose Freddy the fly begins at x is equal to 0 meters and travels at a constant velocity for 6 seconds as shown. Find 2 points, sketch a displacement versus time graph, and then find and interpret the slope and the area of your graph. Okay, so x is equal to 0. He flies for a constant 6 seconds, and he arrives at this later point. Okay, so x is equal to 0, x is equal to 18. The first point occurs at t is equal to 0. The second point at t is equal to 6. Okay. So we're going to go ahead and sketch the displacement versus time graph. These are our 2 points, 0, 0, 6, 18. All right, so displacement versus time, remember whichever comes first in that saying, something versus something else, the something goes along the y-axis and the something else goes along the x-axis. All right, we always put a slash and we put the unit after the variable, so slash seconds and slash meters. Ruler use, scales labeled, appropriate units, and appropriate scale as well. All right, so here we go. We have our first point 0, 0 and the second point 6, 18. Now, with 2 points, you'll always draw a straight line in between them. Generally speaking, you need at least 3 data points to create a line of best fit, right? 3 would be the minimum. In this case, we're just using 2. Okay, so here's the rise of that graph, and there's going to be the run afterwards. So the rise is 18 meters, the run is 6 seconds. So rise over run is 18 meters over 6 seconds. That's 3 meters per second. That's velocity. So the slope of a displacement time graph is velocity. Now let's look at the area under a velocity time graph. Okay, now you're being told that the area under the graph is displacement, and the area under the acceleration time graph is the change in velocity. Okay, so let's see why that is. Here's a velocity time graph. We already saw that the slope of this is acceleration. Now let's look at the area underneath. The area underneath this graph is a triangle, and the area of a triangle is given by 1/2 base times height. So, well, what's the base of this triangle? It's 20 seconds. The height of this triangle is 30 meters per second. So 1/2 times 20, that's 10. 10 times 30 is 300. So 300 meters is how much the object displaced itself after 20 seconds. But remember that the velocity time graph also gives us the acceleration. So if we were to look at the slope, and you can use rise over run in any way. So the rise is 30 meters per second, and the run is 20 seconds. Again, the units have to match, right? Seconds to seconds. 30 divided by 20, so that's 1.5 meters per second squared. And so what you can see is that the velocity time graph actually gives us the most information from all three graphs. The three graphs being position versus time, velocity versus time, and acceleration versus time. All right, so the velocity versus time graph, its slope gives you acceleration, and the area underneath gives you displacement. Now, with acceleration time graph, we'll talk about that in a second, the area underneath of it gives you the change in velocity. Only one thing. Now, with the displacement time graph, the area underneath is meaningless, but the slope is velocity. All right, now we have to talk about something that I said we'd get back to earlier. We saw earlier that Galileo used to drop objects off of the Leaning Tower of Pisa to see if heavier objects would actually fall faster than lighter objects. And the story goes that he would actually stand there and drop all sorts of different objects off the side of the Leaning Tower. Of course, there were no people standing underneath at the time. Otherwise, as we saw, that can be very dangerous. And he actually proved that depending on whether or not you consider air resistance to exist or not, if you ignore air resistance, so you're considering to be in a vacuum, all objects must fall at the same rate of acceleration, which is 9.8. Now, if an object speeds up, so if you drop a penny off the Empire State Building and it reaches a very high speed once it hits the ground, does that mean that if you keep dropping the penny from a higher and higher elevation, that it could just eventually reach the speed of light, which is 300 million meters per second? Is that possible? And the answer is no. Eventually, all falling objects will reach a maximum speed, and that speed is called terminal speed or terminal velocity. And as it says here, this is when the drag force exactly balances the weight. Now, I'm going to show you something. I'm going to do this on a piece of paper, and then the next slide is going to show this with a whale, but I figured this might be a little easier to understand. I know a lot of you probably play video games. I don't know how many of you guys play PUBG, Player Unknown Battleground, but the beginning of the game starts off with you and your teammates flying in a plane, and you have to leave the plane and you have a parachute, and so then you have to land somewhere and start collecting materials. So as the parachute is descending, though, your velocity is, well, it's getting bigger. And if you didn't have a parachute, your velocity would be increasing way too fast for a safe landing. So let's say you have some kind of a plane, okay? All right, so you have some kind of plane, and the person jumps out of the plane. So this plane is traveling forward. All right, so the person falls out. So you know what, instead of drawing a person, I'm going to draw a box, because this might be a little bit easier to draw. All right, when the person or the box is first ejected out of the plane, there's no air resistance acting on them yet. So the only force acting on them is the weight. And again, I draw that coming from the middle of the box because that's the center of gravity. Now, let me start drawing this a little bit to the side now, a little bit further down. As it falls a little bit further down, the weight vector is the same because the object's mass didn't change, so the weight can't change. But there's now a little bit of air resistance on them. So we'll call this force air resistance. And as this keeps falling, right, so over time, the weight is still the same, but the air resistance is increasing, right? Because as this object is falling faster and faster, there's more and more air blowing on it. Imagine you're in a car and you stick your hand out the window while it's moving. Of course, don't stick it out too far. You have to be safe. But if you just stick your fingers out partially out the window, if you're traveling at a slow speed, you'll feel a little bit of air hitting your fingers. And if you travel at a fast speed, you'll feel more air hitting your fingers. There's more air resistance, right? And the longer you fall, the faster your velocity gets. Now, your weight is not changing, which is why the bottom arrow stays the same. But notice the air resistance keeps increasing and increasing until it matches your weight. Notice that now these two forces are balanced, right? Originally you had no air resistance, and then you had a little, and then you had a little bit more, and you have a little bit more, but now it balances the weight. And so what's happening here is you started off with a velocity of 0, u equals to 0, and then here you have v is increasing a bit more, and v has increased even more. But at this point, your velocity can't increase anymore because now these two are balanced. When we start learning about net forces, Newton's second law, this will all make more sense. When you have two forces that balance each other, the object cannot accelerate anymore. And so you eventually, if you can't accelerate, that means your speed can't change. And so your speed becomes constant. So this is the point at which you reach terminal velocity. Now, if you use a parachute, the parachute, what it does is it applies a sudden acceleration. So it suddenly slows you down. Now, you don't at any point actually move up, contrary to popular belief. The only reason it might look like someone's moving up when they open a parachute in a movie is because if the camera is falling with them at the same rate, well, once they open the parachute, they're not falling at that rate anymore. They're still falling, but slower. So relative to the perspective of the camera, the person looks like they've gone up, right? Because the camera is also coming down at that same high original velocity. So we reach the terminal velocity or terminal speed, which is the highest speed attainable. And then that speed just continues until the object collides with the ground. So at every point afterward, these two forces will just always be the same. The weight anyways never changes, but the air resistance force remains constant as well. Okay. Let's go back to the slides. Now this next slide is explaining the same thing, but in terms of a whale. If a blue whale was to suddenly materialize high above the ground and high above the sea, there would be a drag force. So instead of calling it F air resistance, here you can also call it drag. And actually that's a little bit of a shorter way to represent it. W is the weight. So initially there's no drag, and then there's a little drag, and then there's more drag until it balances, at which point the velocity reaches terminal velocity. Okay, last couple of slides, and then we're almost done for this video. Determining relative velocity in 1 and 2 dimensions. All right. Now, whenever we say that a certain object is traveling at a particular speed, it's always relative to something. We might not realize that we're giving a value relative to something, but we are. So if someone's running the 100-meter dash in the track and field finals, and we say that they cover the 100-meter in 12.5 seconds, we calculate their speed, that speed is relative to something. It's relative to the stationary ground or maybe some other stationary object. Right? So in this case, your velocity relative to the pavement might be 60 miles an hour if you're in a car. But maybe your velocity relative to an oncoming car might be 120 miles per hour. If you are driving on the road and there is another car approaching you at the same velocity, or rather any velocity, it appears as though they are approaching you much faster. And that is the case of relative velocity. If you are stopped at a red light and you don't react when the light turns green and the person beside you does, they will start accelerating forward, and it's going to feel as though you are moving backwards relative to how they're moving. Now, relative velocity can be measured relative to any reference frame. Consider cars A and B below. Okay, so A is moving at 20 meters per second to the right, and B is moving at 40 meters per second to the right. Now, relative to you, car B makes you feel as though you are traveling backwards at 20 meters per second due to how fast it is going. Okay, so we can come up with an expression for the relative velocity of A relative to B as velocity of A minus velocity of B. Right? So 20 minus 40. So negative 20 meters per second. Now that formula you can apply in 2 dimensions as well. So if you have someone moving in the y direction, or in this case the negative y direction, and you're moving in the x direction, it works just as well. Okay, in this case, car A is moving at the high speed of 40 meters per second, and B is moving in the negative y direction, hence at minus 20 meters per second. So we can calculate relative velocity exactly the same way. The velocity of A relative to the velocity of B is going to be VA minus VB. What you just have to remember is that now that you're working in 2 dimensions, you have to remember what we learned about vectors in section 1.3. If VA is going to the right and VB is going down, and again, notice the lengths of these arrows. VA is much longer than VB because the vector itself is longer. right? So the longer you draw the arrow, the larger you are representing the magnitude of the vector. But instead of subtracting vectors, we add the negative. So we actually want to do VA plus negative VB. Negative VB is the opposite vector of VB. So it has the same magnitude, but it's going in the opposite direction. So when we add these two vectors, all I do is add them tip to tail. So the tail of negative VB attaches to the tip of VA. And this resultant vector goes from the tail of the first vector to the tip of the final vector. So that is our relative velocity. Now, how do we find that side? Well, we have a right-angled triangle, right? So you find the magnitude of the hypotenuse using Pythagorean theorem. And if you need to find a direction, you can use SOHCAHTOA, since it is a right-angled triangle. In this case, it turns out that our relative velocity is 45 meters per second, and you can verify that with the calculations. Okay, so actually we're going to stop there. We'll leave projectile motion for the next lesson. All right, so that is the end of 2.1 motion, part 1 of 2.